So I thought what we could do is walk through some of the chapter 10 homework, and I'll show you how to do this stuff with R. But let's actually get to some of the actual statistics here. So the first few questions are multiple choice. Okay, so for this one, the idea here with chapter 9 and with chapter 10 is that you're going to use the t-test function. And that's really the star player in chapter 9 or 10. For chapter 10, we're talking about t-tests with two samples, okay, from two populations, I mean. And so there's a few things that we can do here. The first thing is that this is a two-tailed test. So the null hypothesis, I don't even have to think about the rest of these. I don't have to look at them. I know that the null hypothesis has got to be that mu1 is equal to mu2, and the alternative is that they're not equal. So that's part E. So we don't even have to think about any of the numbers or anything there. And so the null hypothesis, the way that the book has it set up, is that the null hypothesis is that the means are equal, and then the alternative hypothesis is that either mu1's less than mu2, mu1's greater than mu2, or they're not equal. And so if it's less than, then it's a left-tailed test. If mu1's greater than mu2, then it's a right-tailed test. And if they're not equal, then it's a two-tailed test. The next thing we need to do is to compute the test statistic. And there's formulas for this. But what I like to do with R is the following. So let me show you in R. If I were to just have two data sets, then everything would be fine. And you could use R very nicely. The problem with this homework is that they give you not the data sets, but they give you the summary statistics of the data sets, meaning they tell you how many data points you have, what the mean and standard deviation are. To use R, it would actually be more effective if you had the data set than if you had the summary statistics. And so what I like to do is I like to just come up with data on my own that has all these values, and I'll show you how to do that. So the first thing that we're going to do is I'm going to define X to be our norm of 19. And if you want to call it X1, we can. And that's because we have 19 data points. Okay. And whenever you use this R norm button, or this R norm function, I should say, this is a function that's going to give you 19 data points that are going to be randomly selected from a standard normal distribution, meaning that their mean is 0 and their standard deviation is 1. Okay, so these are just 19 random data points. Now the mean's not really going to be 0, it's going to be close, and the standard deviation is not really going to be 1, although it'll be close. And so what we have to do is we have to fix that, and then I'll show you how to adjust to get the mean and standard deviation that we want. So the first thing that we're going to do is we're going to subtract. I'm going to redefine X1 to be itself minus its mean. And the reason why we want to do that is that now if I look at X1, I've subtracted this point. I've basically added this 0.188 value to each of the numbers. And so if you take 1.88 and add it to each of the numbers, okay, this is what you get. And we still have 19 data points. I'm going to kind of show you the details here, and then we'll, there's a quicker way to do this that I'll show you at the end, but I want to explain each of the steps. So the first thing is that you subtract the mean. The next thing is that you're going to change the values so that they have the standard deviation that you want. So I'm just going to multiply by 2.3 and divide by the standard deviation that we had. Okay, and so now X1 is going to be just it's going to be the same numbers, just going to be scaled appropriately so that the standard deviation is 2.3. And so if you were to type in the standard deviation of X1, now it should be 2.3 or something really close to it. Okay, when I say something really close, I mean it should be 2.30000, like 16 zeros, and then maybe something else. So maybe there's a little tiny error, but it's basically 2.3. And the final thing that we're going to do is we're going to take each of these values, and remember that the mean of X1 is going to be 0 now, or something close to 0. So here this is 0 to 17 decimal places. And what we're going to do is we're going to shift back so that it has a mean of 11. Okay, and now this data set is exactly a data set with the properties that we wanted. So it's got the right mean, it's got the right standard deviation, and it's got the right length. It's the right number of data points. Okay, and so that's how we do that. And so let me do that. I guess we've already done it to x1, so I'll show you quickly how to do it with x2. You're going to take, here we again need 19 data points because our n2 is 19 again. And then what we're going to do is I'm going to take x2 minus the mean of x2 times the standard deviation of x2, excuse me, times whatever we want the standard deviation to be, which was 2.1, divided by the standard deviation plus 13. And then here's our data set that we want. So just to make sure that it has all the properties, the mean is 13, the standard deviation is 2.1, and it's still got 19 data points. Okay, and here's the numbers. What the numbers are don't matter, but there's the idea. And what we're going to do then is now we can just use the power of the t-test function. So once you get really good at coming up with these data sets, the t-test function is way faster than anything you can do by hand. And all of the parameters for the t-test function are set so that it's two-tailed and 95% confidence, meaning a 5% significance. So all you have to do is type in t-test of x1 and x2. And for this particular problem, it'll give you what you want. Okay, so our test statistic is going to turn out to be negative 2.7991. We're going to round to 3 decimal places, so that's negative 2.799. And what else do we need? We want the critical values. So for the critical values, yeah, let's see. So for the critical values, what we're going to do is we have, so we want to find the cutoff point where up to 0.025, and we have 38 data points in general, so we subtract 2, so 36. So the critical value should be negative 2.028, 2.028, and it's already got the plus or minus in front. Okay. Should I say more about the critical values?
Can you just distinguish between critical values and p-values?
Critical values, yeah, so critical values are values that it doesn't matter what your mean and standard deviation of your data set are. It's just determined by the number of data points that you have and the significance that you want. So if we have a 5% significance, what we can do then is we know that if we take that area and split it in two, there's going to be a left tail and a right tail because it's a two-tailed test. And the left tail and the right tail are each going to have area 0.025. And so this QT function is going to tell us what's the cutoff point so that the area under this t-distribution curve up to this cutoff point has area 0.025. And we determine which t-distribution by the degrees of freedom. And so that's going to be the sum of these two numbers minus 2. Okay, so that's where the 36 came from, is the 19 plus 19 minus 2. So the critical values are determined by, really they have not much to do with the data other than, I guess the degrees of freedom tells you which t-distribution to use, but that's the critical values. P-values are a property of the actual data points themselves. And so if you notice in the t-test, it gives you the p-value. It tells you what that is. And the p-value is basically, what is the probability that your data is at least as extreme as the data that you observe? So what I mean by that is that if you observe something happening, what you want to know is that a rare thing that happened or not a rare thing? And that's what the p-value measures. Okay, so the p-value here says that this is a pretty rare thing that you saw happen. It's probably not happened just by chance. And therefore, since this p-value is less than your alpha, you would reject the null hypothesis. You have enough evidence to say that the null hypothesis is wrong. Okay, so since the test statistic is in the rejection region, we reject the null hypothesis. Okay, does that make sense what I said?
Yeah, that all makes sense. And then do you need to do any different t dot test if it's a pooled t-test versus an unpooled t-test?
Yes, and I'll show you how that works as well. Yeah.
Okay.
So I'll show you that in just a second. So we'll go through a few other examples from chapter 10 because there's some intricacies here. So if it's pooled or not pooled, and if it's a paired difference, we'll talk about that as well. And notice that the t-test function also gives you a 95% confidence interval. It does literally all this work for you. And we're going to round to 3 decimal places. So help me out. This will be negative 3.450, I guess, negative 3.450, all the way to negative 0.550, I think, negative 0.550. There we go. Okay, and so that's the magic of the t-test function. If you want to get a grip on how this t-test function really works in all the different choices that you have, what I would suggest is that you type in help t.test, and then this will bring up a document. So I have a Mac, so this is how it works for Macs. It'll work differently for Windows. It works differently still if you have RStudio. But if you type in this t.test function, it tells you all the different options that you have. And so if we have, we had a two-tailed test, so we pick the two-sided alternative hypothesis, and that's kind of the default assumption. You don't have to say anything if it's two-tailed. Likewise, you can name the confidence level, and it's going to by default think that the confidence level is 0.95. So not much to say there. If it's a paired test, you would put paired as true, but by default, it thinks that it's not paired unless you say otherwise. And also, it's the var.equal being false. That's also the default assumption. It assumes that it's the variances are not equal. And we'll talk about how that works differently for a pooled versus an unpooled t-test. Okay, but this is just a reminder of all the different options that you have for this function. So with that being said, let's get rid of my bar there. So with that being said, let's go through and let's do, this one is very similar. You would want a right-tailed test. And so I think this one's worth just talking about very quickly. Let's do this again. So X1 is going to have 10 data points. X2 is going to have 13 data points. And then we're going to do the usual stuff where we take X1 minus its mean times what standard deviation do we want for X1? 4 divided by the standard deviation plus we want a mean of 16. And so we can check, you can check all the stuff here. And so we'll do the same for X2. So we're going to subtract its mean. We're going to multiply by the standard deviation that we want, divide by the standard deviation that we already have, plus the mean that we want. Okay, and then that should have all the properties that we want there. And then we are going to do a right-tailed test, again with 5% there and a 90% confidence interval. So R in our book do confidence intervals just slightly differently. I'll explain, but R does actually a right-tailed confidence interval differently than it would do a left-tailed and differently than it would do a two-tailed confidence interval. Our book does them all the same. So I'll explain how you do that in a second. But this is a right-tailed test, so that means that we're looking for mu equals for the null hypothesis, and the alternative is that mu1 is greater than mu2. So nothing really interesting there. To compute the test statistic, what we're going to do is do the t.test. We'll do x1 and x2. Notice that I'm using the same terms, but I've redefined them. And then the test statistic is going to be what it is, but just because we may need it, I'm going to look at the alternative as being, I'm going to look at the alternative as being greater. So that's what we do for a right-tailed test. And then I think everything else is the same. So it's still alpha is 0.05. Yeah, and everything's fine. And so
It said we wanted a 90% confidence interval this time, though.
yes, so I'll explain how that works in just a second. You have to do the confidence intervals separately from the rest of the t.test function.
Okay.
And so, yeah, I'll explain, because the way that the book does a 95, the way that the book and R do two-tailed confidence intervals are identical. You just have some interval, and in that interval is you have a 95% confidence that your difference in means is going to lie in that interval. The way that R does a right-tailed test confidence interval is it says, basically you take a 95% confidence interval, and then what you do is, instead of going in both directions, you just go from wherever that 95% confidence interval was to infinity. And so it's a little bit different than what it does, but I'll show you how to do this in just a second. The test statistic we found was 0.660. Okay. This is a pooled test. So let me go back just for 1 second. What is different here? So this is a pooled test. So that means we want x1 and x2 and the they're equal being true, and alternative is greater. I think we lucked out before. I think I made a mistake before and I just got lucky. So let's try this. So it's 0.686. Okay. Because it's
that last time pooled and unpooled were the same t-test?
I think they were the same up to 3 decimal places. So okay. I'll go back and I'll look at that. But I think in the previous example, I should have, wherever it was, I should have added here the var.equal being true. Okay. And so that's, yeah, I think we just got lucky there. Okay, so sorry, I missed that on the first round. And then our critical value, it's a right-tailed test. So our critical value is going to be what's the cutoff point, so that the area up to that cutoff point is, we're talking about a 5% significance. So that's going to be 0.95. So it's QT 0.95. And then let's see, we have how many degrees of freedom? We have, notice 10 plus 13 is 23, minus 2 is 21. So this tells you the degrees of freedom here. So we have 21 degrees of freedom, and then that'll tell you your cutoff point, 1.721. That's your critical value.
And we use 0.95 because it's a right-tailed test.
We did. QT. Yep, you don't. So for the two-tailed test, you had to take that 0.05 and split it in 2 because there were 2 tails. But here it's just 1-tailed, so you don't have to split it.
Yeah, and then if it was like a left-tailed test, you would still do like a 0.05.
It would, exactly. It would be QT of 0.05 with however many degrees of freedom. Exactly right. Awesome. And then you would get a negative value. And then both R would give you a negative value, and my math lab would have either a negative in front, or it would tell you somehow, it would somehow indicate that. And then there's 2 ways to think about this. This is your critical value. This is your test statistic. Your test statistic is not greater than your critical value. Equivalently, your p-value is not less than or equal to your significance. And so that tells you that you don't reject. So since the test statistic is not in the rejection region, we just don't reject. Okay, and then finally, we need the 90% confidence interval. So what I'm going to do is we'll do the same t.test again. And actually, I don't care if we don't need anything about the variations being equal, but I guess we can put it in. And we want our confidence level to be 0.90. And so
we need to add a alternative equals greater or not?
No, in fact, we don't want to do that. When you do confidence intervals for MyMathLab always wants two-tailed confidence intervals, regardless of whether the test was right-tailed, left-tailed, or two-tailed.
Okay.
And so that's the difference. But just notice the way that this worked is that the 90% confidence interval, which is what MyMathLab is asking for in the homework, goes from negative 1.507 to some 3.5. But the 95% confidence interval, according to R, started at the same point, that negative 1.507. It's just that instead of looking at the middle 90%, it's giving you a 95% confidence interval and saying, well, if you have a 90% confidence interval, just go from that to plus infinity, and then you get a 95% confidence interval, if that makes sense, right? It's taking that extra 5% that lies beyond the right endpoint and giving that a 95% confidence interval. So MyMathLab and R do confidence intervals differently. So we just have to run a separate test, and it's always going to be a two-tailed confidence interval that MyMathLab wants. So we'll want negative 1.507. So negative 1.507 to 3.507. And that should do it. Yeah. Okay. And so that's how we do that for the pooled test. And what does this problem say? For this problem, I'm a little bit bothered that they don't give us the number of data points.
Oh, you have to click the icon, and then there's 12 data points in that, or there's 10 data points in that.
This is even easier. So what you can do instead is you can take, say, fraud and define that, using all the values, go through, and you can actually just do it in this case. You don't have to come up with the data like we did before with the X1 and X2. You can just actually type in all the data, and then it's exactly like the ones we've done so far. So that's all I'll say about that. Yeah, this is exactly the same question as before. Same question as before. Yeah, they want a 90% confidence interval. So that's literally what we just did. And now here's the first one where it's non-pooled. Okay, so R is going to, by default, assume that what we want to do is a non-pooled t-test unless we say otherwise. So if it's pooled, you need this var.equal being true. And if it's non-pooled, you just don't include that. So you don't need to include that at all. And so we can just do basically what we did before. Let's do it. So I can show you how to do this kind of super quickly. So our X1 is going to be 10 data points. And what we'll do is we'll take each of these values and subtract the mean, multiply by the standard deviation that we want, divide by the standard deviation that we have, add the mean that we want. Hopefully that all makes sense and I'm not going too quickly.
Yeah.
So we're going to take the values. Oops, and I forgot to tell what X2 is. I want 10 data points. Because if I didn't redefine X2, it would think that X2 is the value that we wanted in the previous problem, which we don't, because that's got the wrong number of data points, probably. Anyway, so X2 is 10 random values. And then what we're going to do is we're going to take X2 minus the mean times the standard deviation, which we want is 4, divided by the standard deviation that we had, plus the mean that we want. And there's our X1 and X2. And then we can do the t.test of X1 and X2. And this is two-tailed with a 5% significance, 95% confidence. So we only have to do this once. And here's all the values that we need. So our two-tailed test is going to be that the null hypothesis is always that the means are equal. The alternative for two-tailed is that they're not equal. And then we can find the test statistic, which is negative 2.121. And then we can find the critical values. And the critical values will do the 0.025 trick. Here, our degrees of freedom is, so the way that the book does this is that when you have a unpooled t-test, or non-pooled, however they say it, the degrees of freedom is quite a mess to calculate. So if you look on the formula sheet, there's a value, capital delta, which is just kind of a mess to evaluate. But that's this number that you get from the t-test. And so what you do for the degrees of freedom is that you assume that it's going to be this value, and now I'm doubting myself, but it should be this value rounded up to the nearest integer. And so we should have 14 degrees of freedom. I think it's rounded up. It's on the formula sheet, actually.
I was running it down in all my tests. It might be rounded down.
It might be rounded down. I'm trying to, it's always going to make you do the most conservative thing. And so I guess the conservative thing here would be that you would have less data. So probably it does want you to round down. I think that's right. It is on the formula sheet though, whatever choice it wants you to make is there. And this should be 0.025. And then that'll give you your critical values. So this is negative 2.160. And this is two-tailed, so by the symmetry of the t-distribution, it'll be the plus or minus of that value. Yeah, so it is rounded down. Thank you. And then you want to know, do you reject or not? And basically what you're going to do is you're going to look at your, there's two ways to do it. You can think about, does this test statistic lie within the critical values? And if this test statistic is in the, between the critical values, then you don't reject. If it's outside, then you do reject. Or I just like to think of the p-value. If the p-value is greater than your significance, our significance here is 0.05, and so our p-value is greater, then you don't reject. Okay, so here we don't reject. There is not enough evidence. And then finally, I just want to point out that two of these answers are nonsense. So the way that a hypothesis test works is that, just a quick digression here, basically science is comprised of, like, I think of it as tentative facts, right? You have a bunch of things that are tentatively true. They agree with everything that we know about the world, but stuff can change at any point. And the way that it changes is that if you have enough evidence, then you know that something's wrong and you remove it, okay? You can never prove something right, if that makes sense. All you can do is just pile on more and more and more evidence that agrees with what we know, but that doesn't mean it's right, because maybe in the future we find something out and that actually means that some small part of it at least was wrong. And so that's the kind of tentative nature of hypothesis testing as well. So the point here is that you can either reject the null hypothesis or you do not reject the null hypothesis. And you reject the null hypothesis by saying there's enough evidence to know that it's wrong, or you don't reject the null hypothesis by saying there's not enough evidence to know that it's wrong. And those are the only options. So the point here is that B and D are the only reasonable answers. So you can either reject because there's sufficient evidence, or you don't reject because there's not sufficient evidence. Okay, so in this case, A and C are nonsense. That's never the answer. So whenever you don't reject, it's because there's not enough evidence. Okay, does that make sense? At least a little bit? Okay. Otherwise, this non-pooled stuff is exactly like the pooled questions.
Except you don't have to do the very equals equals true.
Oh, I forgot the confidence interval, but that's just this part. So, I mean, we can just enter that in. It doesn't matter. Yeah, the only thing that's different is that you don't have to put in the var.equal being true. Okay, you can just leave that off because by default R thinks that that's false. I don't think there's any other real tricks here between pooled and non-pooled.
I don't think there's oh, I guess the last two problems might have paired on the homework. If we could just go over that really quick.
So there's two ways that you can do a paired test. So here's the two ways that I like to think about this. Let's just take, in this case, there's the data sets are small enough I can just record them here. So let's call this population 1. And so the numbers here are 8, 23, 6, 10, 20, 13, and 24. And whenever I manually type in something, I always just like to verify that I didn't miss anything. give it a little look over. Yeah, so x2, the population 2 is going to be 6, 22, 3, 4, 16, 14, 21. Okay, it's important to put them in the right order because you're pairing them up, so they have to be paired with the right other value. Now, there's two things that we can do. If you go back to the help t-test function, there's a paired command. Okay, so you could do paired equals true, and then basically keep doing what we were doing before. So if we want to find the test statistic, what we would do is we would do t.test x1, x2, paired equals true. That'll give you the test statistic of 3.057. Okay, so that's one way that you can do this. The critical values are going to be found just like they would before. So we have a 10% significance, our alternative hypothesis. So we have a two-tailed test. And so what we're going to do is we're going to look at, we take that 10%, we split it in two, and then we look up the degrees of freedom that we have. In this case, the degrees of freedom is the number of pairs minus 1. And so our critical values are going to be negative 1. I already forgot what it was, negative 1.93443 and 1.943. Okay, so that's how that works. And then our test statistic is outside, it's beyond the critical value. So that means that we reject, there is enough evidence, and that's it. Okay, so that's really all you have to do for the paired test. But I also just want to say that when you do a paired test, all that really is it's a one population t-test where your population is the difference between the two. So if I call D, so X1 was the 8, 23, 6, 10 numbers, X2 was the other set, and then I just define D to be their difference. You can also just do a normal chapter 9 test. This is a t-test on D. And then let's see, what did we need? We needed a 90% confidence. So our conf level was 0.9. And then this will give you literally the same test statistic, your degrees of freedom, your p-value, all that will be the same. I think in the previous example, I might have forgot to say, you'll get the wrong p-value here because I forgot to say that we wanted a 90% significance. So it has a 95, but the test statistic is the same regardless of what the confidence level is. But anyway, so that's two ways to do the paired t-test stuff. You can just do it as a one population test on the difference, or you can add in the code in R, you can add in this paired equals true command, and then that'll do that. Does that make sense?
Yeah, that all makes sense. Thanks so much for going over this stuff with me.
No problem. So like I said, I'm recording this because everybody will have this question, whether they know it or not.
Yeah.
Yeah, so there you go. So I'll stop recording here.